Hello and welcome to Data Science for Ecologists in R. In the last video, we concluded the theory part about the linear model by learning how to make inferences about the true model parameters. In the following videos, we will need this theory knowledge to understand what we are doing when we fit a linear model using R. As always, we will start with a very simple example. More specifically, we will use the blood pressure data from the last video so that you can see step by step how the results from the last video were obtained in R. First, we load the car package. This is a package that provides some additional functions to deal with statistical models. But we actually only need one function from this package. All the other functions we will use are available without loading any extra packages. So let's now load our data and see how it looks. As we already know, there are two numeric variables, the blood pressure change and the drug dose. Since there are only two variables, the best way to get an overview is to simply create a scatter plot of the data. If we do this, we get the same plot as in the last video, where it looks like there might be a negative linear relationship between the drug dose and the change in blood pressure. Let's now see how we can fit a linear model to this data. The R function for this is lm, which takes as its first argument a formula. This formula specifies the linear model we want to fit. In this case, we want to fit a simple linear model with the blood pressure change as the outcome variable and the drug dose as an explanatory variable. We do this by writing blood pressure change tilde drug dose. In general, the variable on the left side of the tilde symbol is the outcome variable, and the variables on the right side are the explanatory variables. We don't need to explicitly include an intercept in the formula. This will be done automatically. So the model that will be fitted here is blood pressure change equals beta 0 plus beta 1 times drug dose. With the argument data, we can tell the function from where the variables should be taken. In this case, they come from our data frame dt. If we run the lm function, it returns a model object that we can save in a variable. In this case, the variable model. Let's now see what information we can extract from this object. The first thing we can do is to simply print it. This returns the least squares estimates for the intercept and beta 1, which we can use to draw the estimated linear function in our plot. However, we learned that we must also take the variance of these estimates into account. For this, we can use the summary function. The summary function outputs quite a lot of information about the model. So you should keep in mind that the important information can be found under coefficients. Here we once again see the parameter estimates for the intercept and beta 1. And furthermore, we get the standard error of these estimates. The standard error is simply the square root of the variance of the parameter estimates. The variance of the parameter estimates, or equivalently the standard error, can be used to obtain p-values. These p-values can be found in the last column of the output. But keep in mind that p-values can only be calculated by assuming a specific true parameter value. The summary function outputs the p-values under the assumption that the true parameter values are 0. For example, the output for beta 1 can be read as follows. Under the assumption that the true parameter value is 0, the probability to obtain an estimate that is at least as extreme as minus 0.4217 is only 4.38%. Alright, this is what I think is the most important part of the summary output. Of course, there are also other things in the output that we could talk about, but I will leave that for you to explore if you're interested. One thing that the summary function does not return are p-values for true parameters other than 0. For this, we can use the function linear hypothesis from the car package. In the function call, we have to specify the two arguments hypothesis matrix and RHS, which is short for right-hand side. These arguments can be read as follows. 0 times beta 0 plus 1 times beta 1 equals minus 0.2. In other words, this line of code calculates p-values for the hypothesis that beta 0 equals minus 0.2. Just as in the summary output, the p-value can be found in the last column. We can also verify that the summary function calculates p-values for the hypothesis that beta 1 equals 0. If we change the right-hand side to 0, we get a p-value of 0.04384, which is the same p-value that we obtained in the summary function. Apart from individual p-values, we might also be interested in interval estimates. For this, we can use the confint function. By default, it returns 95% confidence intervals for our parameter estimates. If you want to know how intervals for other confidence levels are obtained, you can read the function documentation. Alright, now that we know the R functionality to deal with linear models, we can look at a more complex example in the next video. See you soon.